All right, teachers, future teachers. We are going into chapter 11.2, which is still more of our geometry stuff. So let's go ahead and get into that. Let's get into the PowerPoint. Lots of definitions in this section. Lots and lots and lots of definitions. So, but this is actually a section that I think you will understand can be done a lot in any of y'all's age levels. Okay, so let's go ahead and start the PowerPoint. All right, so here we have chapter 11, Introduction to Geometry. Okay, and again, let's rock right on into some of this. It can be helpful. All right, so we're going to be talking about curves, and a straight line is also considered a curve, polygons, and symmetry. We're going to deal with simple, closed, and convex curves and concave curves, different types of polygons, naming triangles and quadrilaterals, the hierarchy about polygons. We'll talk about what that means, and then dealing with symmetry. Okay? So we have what's a simple curve, a curve that does not cross itself. It has a starting and a stopping point, and it may actually end up being the same place. Okay. What is a closed curve? A curve that starts and stops in the same place. Okay. We'll show kind of some examples. A polygon is a simple closed curve with sides that are line segments. Okay, so again, a curve can be a line, it's just a straight line, right? A straight curve. And then you have simple curves and closed curves, and a polygon is a closed curve, which means the curve starts and stops in the same spot. Okay, but they're made of not what you think of curves, but as straight lines. All right, convex curve says a simple closed curve with no indentions. The segment connecting the 2 points is an interior of the curve who's wholly contained in the interior of the curve. Okay, and then you have the difference of that, which is a concave curve. Simple closed curve that is not convex, it has an indentation. Okay, the term indentation is kind of interesting for the fact that when you have something convex, it has, let's do it this way, okay? Something like this is kind of concave because of this indentation, okay? Something like this, convex, okay? That's convex, and you have your concave, okay? Something like, let's try to get another shape for you. If I can do it this way. That's again concave or convex. So let's try this one. Let me draw one. See how good I can draw this one. Okay, so when you have something like this, concave. This one's concave. It indents heavily in here. Okay, these are concave. These are convex. Easiest way to tell the difference between the two is if I take a line and I can go in and out and back in again to the inside the figure, then it is concave. Notice if I go in, then I go out, but I don't come back in. Convex. Okay, it's probably the easiest way I know how to tell people how to do. All right. All right, so just some naming. Okay, this here, this is a curve. It's simple. It starts in one place, but it ends in a different place. So it's not closed. And then none of these else can work. Here you have a curve that is not closed, so it's simple because of that gap. But here it's closed. It's simple and it's closed. And once you know it's closed, then you can look. Is it a polygon, convex, concave? and it's concave because I can draw that line through here. And then a circle, simple, starts in the same spot. It's closed because there's no gaps. And it's convex because if I do that line drawing, once I go out, I don't go back in again. All right, so closed, starts in the same spot, okay, but it is not a polygon, okay? Doesn't make it convex, okay? Well, if we go back to convex, it is a simple closed curve, okay? So if it's not simple, it can't be convex or concave. So these two have to actually be checked. Okay, so here I have a simple. It's closed. Is it a polygon? Okay, does it made up of straight lines? Yes. Is it convex or concave? These two cannot ever be checked at the same time, but it is convex. There's no caves in. This would be your cave in right here. All right, so every simple closed curve separates the plane into three disjoint subsets: the interior, the exterior, and the curve itself. Meaning, okay, here's the interiors inside, the exterior is out here. The curve itself is the actual border, the line. This is the curve itself. This is a polygon because it's made of straight lines and it's closed, right? All right, so in polygons, you have sides and you have vertex. This too would be a vertex. This too would be a vertex. Okay? So I'd have a vertex here and a vertex here. Okay, so you have three vertex, one for every corner. All right, so what do we know about polygons? Well, we can name them, okay? You should know 3-sided is a triangle. 4 is a quadrilateral, not a square, not a rectangle. It's called a quadrilateral. We'll talk about that in a little bit. Pentagon has 5 sides. Hexagon has 6. Heptagon has 7. 8 is an octagon. 9 is a nonagon. Decagon is 10. Don't see hendecan very often, 11, but you do see dodecagon is 12. And then anything really after 12, we pronounce as an n-gon. So if you have something with 18 sides, it would be an 18-gon. All right, so interior angles, and we're going to show some pictures of this. You have in every polygon, you have interior angles, which is inside made up of the angle of, two rays that we looked at. It has a common vertex. We have an exterior angle of a convex polygon. And we have what's known as a diagonal. Okay, a diagonal goes through the polygon. So give you some perspective. Okay, we have the interior, which is everything inside. This is the interior. Here's your diagonal. So you have a diagonal here. You also have a diagonal that would come here. Now, your diagonal is not allowed to leave the interior of the polygon. Okay, and then you have the interior angle right here. Made up of two sides. There's an interior angle over here. Here's an interior angle over here. Here's an interior angle here. And the exterior angle is on the outside with an extended line. Notice this is not here. It's an extended line. In fact, you can even go this way. Here's another line. That would be an extended angle. That would be exterior. This would be interior. All right, congruent parts. Parts of the same size and shape. That's important, okay? Things that are congruent have the same size and the same shape. Two line segments are congruent if the tracing of one line segment can be fitted exactly on top. Two angles are congruent if they have the same measurement, same degrees, same size. All right, so here we have the symbol. Okay, this is saying the segment AB is congruent to the segment CD. Here's CD and here's AB. So this is called a congruent mark. Okay, so it tells you that AB is the same length as CD, but we don't really talk about length, we talk about size and shape. Okay, then you have these two angles. This angle is 180 degrees, this angle is 180 degrees, which means the two angles itself are congruent with each other. Okay. All right, regular polygons. Okay, in a regular polygon, all sides are going to be the equal length, and all angles, interior angles, are the same. In other words, it is equilateral and equal angular. There you go. All right, so this is a regular pentagon. All the sides are the same, all the angles are the same. These marks, these are congruent marks also. Here you have a regular hexagon. Has 6 sides, 6 interior angles that are all the same degrees, and 6 sides that are all the same length or distance. All right, now we talk about names of triangles. Okay, we have what's known as a right triangle. It has one right angle in it. Now, if you remember back in your geometry classes, all triangles have to add up to 180. So one of those angles is 90 degrees. You have an acute triangle, which all the angles are acute. Okay, now remember what acute means. Acute means that they're all less than 90 degrees. Okay? And you have obtuse, containing one obtuse angle. Now, that obtuse angle has to be greater than 90, but less than 180. Okay, so it's in between 90 and 180. All right, scalene triangle. Scalene triangle has no congruent sides. All the sides are different. Isosceles triangle. 2 sides at least are congruent. And equilateral triangles, they're all the same. Now, the tricky part about this is because of this term, at least, then this is an isosceles triangle, and this is also an isosceles triangle because it has at least 2 sides that are equal, even though we call it equiangular or equilateral. All right. Trapezoid. So we get into quadrilaterals. Quadrilaterals means it has 4 sides. And quadrilateral has at least one pair of parallel sides. Notice here that one's parallel to that one. Okay. Okay, a kite is a quadrilateral with 2 adjacent sides congruent and 2 sides, other 2 sides are equal. So notice the shape. 2 sides are congruent. These 2 sides are congruent, but they don't alternate. They have to be on the same side, basically. All right. So isosceles trapezoid. Okay, where a trapezoid has one set of parallel sides. Okay, you can see them here. All right. So you have one set of parallel sides. Here's a parallel with this. These two are not parallel. So, but so that makes it a trapezoid. Okay. Now, these happen to be equal this time. That's what makes it isosceles. Okay. Parallelogram, quadrilateral with each pair of opposite sides. Okay. So, things that we're going to find out later. So to be a parallelogram, these 2 sides have to be congruent. These 2 sides have to be congruent. The first 2 have to be parallel to each other. And the last 2 have to be parallel to each other. And that makes it a parallelogram. A rectangle is a parallelogram with right angles. So it has to have all right angles and the sides have to be opposite each other, are congruent and parallel. Rhombus is a parallelogram with two adjacent congruent sides. In other words, these two are equal, those two are equal, okay? But by rule, it says the two adjacent sides. Well, what's adjacent again? Well, next to each other. So we're talking about this side congruent to this side. That's your adjacent sides, and that makes it a rhombus. Square is a rectangle with two adjacent sides congruent. All right, hierarchy. So what is hierarchy? Well, it's how they're all related to each other. So how are they all related to each other? Well, a polygon can either be, you have triangles and quadrilaterals. Triangles have three sides, and you can have them as scalene or isosceles. Scalene, all the sides are the same, or are different. Isosceles, two are the same. And then if it's isosceles, it could be equilateral if the third side is equal. Now, that's for three. So for four sides, I go quadrilateral. That splits up into a kite and a trapezoid. Okay, a kite has the sides right next to each other are the same. So only the rhombus and the square have that after that. Okay, but a trapezoid has the one side the same. Okay, so then you have or parallel, and then if both opposite sides are parallel, they're parallelogram. Okay, it could be an isosceles trapezoid. And then from parallelogram, you get rectangles and rhombuses for different reasons, and then a square is the basic. Okay. Now you can't necessarily work your way down this list, but you can work it up. In other words, if it's a square, then it's also a rhombus and a rectangle, which would make it also a parallelogram, a kite, or an isosceles trapezoid, which would make it a trapezoid, which means a square is a quadrilateral. Okay, so a rectangle can either be called a parallelogram or isosceles trapezoid, but a rectangle can never be a rhombus. So since it can't ever be a rhombus, then a rectangle can never be a kite. Okay. All right. Lines of symmetry is what cuts a figure perfectly in half and equal on both sides. Okay, you have a line of symmetry as L. So notice this one has three lines of symmetry. You can cut the figure in half perfectly. This one only has one. Okay, now this one has a bunch. It has got 1, 2, 4, 5, 6, 7. Okay, so it's got a bunch of different lines of symmetry. And then here's an awkward one that's right down the middle, so it's only got one. All right, so how many lines does each of these have? Okay, well, if you look at this here, I have a hexagon. This hexagon has 6. 1, 2, 3, 4, 5, and 6. Has 6 different ones. Okay, this A only has the one right in the middle. This kind of weird shape, oval, has 2. It's right down the middle, cuts it in half. This one cuts it in half. Any given time, it has 2. And then the Z has none. Cannot cut it and have the exact same figure on both sides. All right, rotational symmetry. So rotational symmetry is also known as turn symmetry. Okay, when its trace of figure can be rotated less than 360 degrees about some point. And then the turn center so that it matches the original. So what you do is, here's my center, and I rotate it around it. So this A, when I rotate it, goes here to B, and then it rotates one more time and gets here to C, but in all 3 turns, it gives you the same figure every time, just different lettering. So, how do I figure that? Well, if it's got 3 turns, got 360, so you take 360 divided by 3 and get your 120 turn. Same thing here, 120 turn, because it's got 3 points. So determine the amount of the turn rotational symmetry. Well, you can go right here, 1, 2, 3, 4, and 5, right? 2, 3, and 4. I got 4. Okay, so there is my 4. Now, how do I get that number? Well, you would take 360 Okay? And this is going to be 1 turn, 2 turns, 3 turns, 4 turns, 5 turns. So it's got 5 turns. So we divide it by 5. I get 72. So the first turn is 72 degrees, and the next one is 144, and the next one is until we get to 360. So here, how many times is this turn? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it's 12. Nope, less than that. I recount it. Let's go here. Let's draw that again. Losing my focus here. So here is 1, 2, 3, 4, 5, 6. So there's 6 turns. So that's 60 degrees on each of them. And then this one, I don't think it has much of anything. It has 1. Get back here. Yeah. There we go. Gotta keep clicking. All right. Point symmetry has to have a rotation of 180 degrees. 3-point symmetry. So, can I turn it halfway around? Can I turn this halfway around? Yes, it does. Can I turn this one? Yes, it does. Can I turn this one? Yes, it does. Can we do this one? Just one. Okay. Oops. All right. All right. Since geometric figures in a plane can be classified according to the number of symmetries. Now, we're not going to do a whole lot on this. We can use line symmetry and turn symmetries to consider. Just consider a triangle described as having exactly 1 line symmetry and no turn lines of symmetry. What could it look like? Well, it looks something like this. Okay, has 1 line of symmetry, so it's isosceles. Okay, and no turn symmetries. In other words, you cannot turn to a certain degrees except for 360. Something that has a turn of 360 has no turn because 360 gets you back to your beginning. Okay. All right. So we got through that. So lots of terminologies. I hope that helps to get you through that next section.